this assessment, we're given a C13 NMR that shows only 2 signals, told that it corresponds to a molecule with the molecular formula C6H14O, and asked to predict the structure. Now, C13 isn't that great as a standalone technique for structure elucidation, so there's going to be other information that we need here. If we had a proton NMR and an IR, that would help even more. We don't. But what information do we have in the molecular formula? Well, we have the index of hydrogen deficiency. And if we calculate the index of hydrogen deficiency, 6 times 2 plus 2 is 14 minus 14 is 0. Our index of hydrogen deficiency here is 0. That's a big piece of information. We're getting a lot there because what we know is there are no functional groups in this molecule that contain pi bonds, and there's no ring, right? So when we looked at this oxygen, we might have imagined a carbonyl. We don't have a carbonyl. With an index of hydrogen deficiency, to review, we have no ring and we have no pi bonds. And so what does that mean? That lone oxygen, the 2 possibilities are either an alcohol or an ether. What other information do we have? Well, there are 6 carbons in the molecule. If all 6 carbons were unique, we would expect to see 6 signals. And yet, we only see 2 signals. What does that tell us? Well, that tells you that there must be symmetry in this molecule. There's going to be symmetry in the molecule because these 6 carbons are being represented by just 2. And even though we can't use integration with C13 in the same way that we do with proton NMR, the fact that these 2 signals are of similar height means that we might have 3 of each, or maybe 4 of one, 2 of the other. Similar numbers. What's the last thing we know? Well, in terms of the chemical shift, one of the carbons is going to be between 0 and 50, and so that means it's not attached to any electronegative atom. The other one is between 50 and 100. So the one that's here is going to be the carbons that are represented by this signal are going to be the ones that must be attached to oxygen. Okay, they must be attached to oxygen. Let's call that signal A, and this one signal B. Carbon A, of which there are probably 2, is attached to oxygen, which is also attached to carbon A. So that uses up 2 of the carbons in the molecule. How many other carbons must there be? Well, there must be 4, and those 4 must be identical. And so let's keep the molecule symmetrical and put a CB on each of CAs. There would be symmetry in this molecule. These 2 CAs are the same, 1 signal around 65 hertz or 65 parts per million. 4 CBs, all the same, 1 signal between 0 and 50. Now, I've only shown these as carbons. How many hydrogens are attached to each? Let's draw in the hydrogens. Well, this one, CB, each CB would have 3 hydrogens. Ca, oxygen, carbon, carbon, 1 hydrogen on both CAs. Each CB, these will also all have 3 hydrogens. We're kind of drawing all of these in just so we can now count and see, do we have 14? 3, 6, 9, 12, 13, 14. 6 carbons, 14 hydrogens, 1 oxygen, symmetrical, so 1 signal for Ca, 1 signal for Cb. This molecule, drawn the way we draw organic molecules, is isopropyl ether.